The topic for today's Tech Talk is the 3D digital backbone titled Your Pipeline, Your Rules. Thank you for being here. I'm Jean-Christophe Leducq, Lumiscaphe's CEO. To start with that Tech Talk, we will look at several problems in usual 3D pipelines and workflows and walk through these problems to explore what we can do to solve them. To begin with, the first issue is a projection problem. When you create a realistic 3D model using your favorite 3D software, transferring that 3D model to another software typically requires the use of an intermediate file format, such as FBX. During this process, you will face what is known as an uncontrolled projection to FBX from your original software. The term uncontrolled refers to the fact that the exporter responsible for converting your initial data into the FBX file format will apply its own set of rules for this projection. We refer to this as a projection because it results in a loss and transformation of information. It's termed uncontrolled because the transformation is not performed by your own code, but rather by the embedded FBX exporter in your traditional software. Once you switch to another software, you encounter a new set of challenges because when you export from FBX or import into the targeted software using that FBX file, there's a lack of control over the data projection. This results in two main biases that can compromise your original information. While it is possible to restore some of that lost information, it requires additional effort to correct the discrepancies. That's better than nothing. However, we often refer to this process as exporting your information and praying that the best information will be preserved. Now let's consider what it could be like if we didn't have to worry about the initial tool used, regardless of what it is. If I could directly project from any initial tool to my destination tool, applying my own projection, I understand that some information may be lost or transformed in the process. That's an obligation, because this is not the same universe. So, I have to do that projection. But if I can control the projection myself, and if I have control over the source code of the export from A to B, then I can master what I will have in the final software. So, the idea here is it would be interesting to have one projection, one bias, but my bias or your bias. You choose. Second problem, collaboration. Imagine, once again, you are in your favorite 3D software, and you do some work and change the color of the car, and you save your work. At the same time, another user is taking the same initial file in the same tool, let's say, for example, in Blender, why not? He will change the wheels of the car, and if the rule is to save the final results on the file server, you know what will happen when the destination is the same. So, the last save will win and will crush the initial save. So, we have a problem here. How can we manage that if we have two users working from the same car model doing parallel work? So, imagine once again if I use the initial yellow car paint and I change its color to red. In parallel, my colleague does the same on his side, working on the wheel. And one tool can compute the delta between the two scenes and then reapply and inject the delta into the initial scene. Then the result is a combination of the two pieces of work, and we have a single save that merges and unifies the two different workflows, finally. All of that in the same software. Now, I want to imagine the same thing, but with offline work. Imagine that the two colleagues are working at different times, in different locations. They are not connected to a server because they are offline. And then they come back on Monday to the office and they want to merge their work. I want that to work. Imagine that. It might be cool, especially if this is in my traditional 3D software. So, for collaboration, the idea is, if I use any legacy software, do I have a way to combine those different workflows in the same database? Another one, synchronization. Imagine we start with sketching, for example, in CATIA, and then export it here in Patchwork 3D, a Lumiscaphe 3D authoring software, but it can be Blender or VRED, any kind of 3D software. We go from CATIA to that secondary tool, and then I create in Patchwork 3D or in Blender some materials, a PBR material, or some lighting, and it has a very nice final rendering. But the guy who initially creates the car in CATIA makes some changes and creates new wheel models, new parts. And then he says, okay, great, now we can do the job and update the car or create a new version of the car with an option for the wheels, for example. What I can do is re-export from CATIA to Patchwork 3D or import. And then here, I have a problem because I have two versions, and the work I made previously with the previous car, we cannot simply merge these two different kinds of scenes and changes. So very often, the feedback we receive is, I have to redo all my work. I have to patch up the scene and change things. It's a lot of work. It's difficult. So imagine that problem. We said that the downstream work is destroyed by the new export. So That means you have to start your work over again. So now, imagine the same workflow, but this time, once again, we compute the delta between the two initial scenes in the same software. After that, if you want to export, we reapply the delta that has been computed on the final scene. Then we can imagine updating the downstream work. Here, we don't lose our work this way. We can upgrade the car or create a new version of the car very easily. Inside that is a non-destructive propagation during the synchronization between software tools within a workflow. Now, let's consider what we call the digital visual twin. It means that you are in a company and you have your own model that represents a visual twin. It means all the information needed for your company to describe your product, configurations, materials, parts, shared assemblies, and so on. That's typically what you have in PLM datasets. And what is important is that we see that for each manufacturer, you have a specific dataset. Each manufacturer uses its own concepts, tools, structures, and workflows, its own standard schema, and its own rules. There is no unified system and workflow. So, that's the first statement. We must assume that the digital ecosystem is specific to each manufacturer, and I think that's better that way. But for doing your job, you need the best tool in your opinion. That's why it's always a specific workflow for each manufacturer. So typically, I have my digital visual twin model, and I will use several 3D software around it to create a 3D model, its parts, its materials, and to do final rendering. The problem is that we use all this software. As a manufacturer, I cannot re-implement all the software. It's a very difficult task. So I use the best tool for each job. And the main problem is that by using all this software in my workflows, I lock my information in each silo of each software ecosystem. And the problem is, after that, how can I connect my digital visual twin identity to this different kind of information when this data is spread across different silos and cannot be combined or composed? So basically, we can say in that case, there is a factual issue, a lack of information continuity that will break my workflows and my natural information flow within the company. So that's the main problem we have. We met a lot of people who explained, I have interoperability problems. I have a problem combining all the information and running my process. So now, imagine a world with a uniform layer that gives the ability to access and compose all datasets, all your tools, through the same layer. And you can access the internal information of all these tools to compose your own information. So take all the same tools and say that now they are connected to that layer of intercommunication. And now I have an internal concept of material for my car, for example, such as the fabric manufacturer reference. But what I can do in that layer is connect my specific information to a very specific piece of information that implements this concept of material in Autodesk VRED, in Patchwork 3D, or in Blender, for example. So that direct connection means that we are now all talking the same language. I can compose all this information natively and create what we call a metastructure that saves all the context and gives references directly to each fragment of information in each silo of each software. So we can imagine how useful that would be for big projects. So for composition, one platform can access every piece of data natively, directly. Data is one thing, but a workflow is also very important. Here, for example, using the same tools we have seen, we can connect all the different tools and build workflows and pipelines to add value, convert information, and get a result for visual representation, such as car or product configurators. But building such a workflow is very difficult. It's technically hard and expensive to maintain. Why? Because we have the problem of siloing of information, but we also have what we call the 70-30 reality. Which means that when you build a software ecosystem, the typical software stack is built like this. You have a first part that is business logic, the intelligence that drives your workflow, and then the second part is software infrastructure, meaning all the technology needed to implement your workflow. Business logic is usually less than 30% of the source code, and so the infrastructure is more than 70% of the source code. So, the problem is that you are paying for plumbing, paying for the infrastructure, for the technical layer, not for business logic. But what is very important for your business is business logic, the idea that represents 90% of the value for your business. So once again, we can imagine a world where we have a data OS that takes care of all the problems we have seen previously, able to synchronize software, legacy software, your software that are obviously siloed. It can be connected to the data OS using drivers. Thus, they can connect to each other. It's very easy for you to implement workflows and connectors between the different datasets. Imagine a world that takes care of synchronization, collaboration, and versioning just for you, a world that takes care of problems that you usually cannot handle. In that world, you would write only 30% of the code for business logic. You will focus on that. But what we hope in that case is that you can reduce the costs of maintaining such infrastructure by 10 times, because all that plumbing is very costly to maintain. And you have a lot of technical debt on that code. So this is very difficult to manage otherwise, unless a data OS takes care of this for you. You don't have to imagine it anymore, because we made the digital backbone. Basically, the digital backbone is a data OS built for 3D product teams to solve all these problems. You have drivers that connect, let's say, Unreal, OpenUSD, or Blender to the digital backbone. You have a native representation of all the information in the digital backbone, and you can access it simply. It's not easy to access legacy software information natively, because it's enclosed in a silo, it's a black box, so it's locked. So here we unlock that. We expose native data information from a legacy application through the drivers, and the digital backbone gives you bridges to connect and convert data from one dataset to another, or to project one dataset to another, or to create a metastructure and create references from one dataset to another. Here, for example, in green I represent your datasets, because you can create your own data structure, your own schema, and connect your schema to Blender, CATIA, or Unreal schemas, and create what we call a metastructure. And where are we today? I presented this concept at Laval Virtual last year as well. We have developed an Unreal Engine driver that connects natively to the digital backbone. We also have Patchwork 3D now connected to the digital backbone, of course. VRED, USD, a very significant standard for representing 3D information, V-Ray rendering engine, Blender, and Python. Python is natively connected to the digital backbone. So you can write your bridges, your projectors, or your transformation code in Python. This is very easy. Benefits are significant because it saves a lot of work for the people who created these workflows. And finally, we also created an MCP driver for Claude that gives you the ability to connect AI like Claude Code to the digital backbone. Let's say we can prompt Claude or Claude Code, "Can you change the color of the car in this model?" Then Claude finds the right information directly and changes the car color in any model into the digital backbone. It's not over yet. This is just the beginning. We are working hard on all these drivers and bridges, providing customers with solutions to fit their needs. Here is a typical case study in which we demonstrate using 4 ecosystems and 1 pipeline. We start with Patchwork 3D because it is connected to the Renault marketing department and is used to create the digital visual twin of all Renault car products in our software. Here, we are using the latest Renault Twingo model. We could state, okay, let's go and project using digital backbone Renault Twingo information into Blender. This is a demand from Renault. Then, once we have done that, we want something more complex. From Blender, we want to project information into VRED. Why? To show you that, we use this simple example. We can go from Blender to VRED, a Patchwork 3D competitor, and then go from VRED to Unreal Engine. Here we have a complete pipeline. This pipeline, utilizing its digital backbone capabilities, is fully synchronized. I manage each projection seamlessly between different software, so I can exactly master what I will do from Patchwork 3D to Blender and how to make material substitution instead of material creation, because it's better in this case. So I will master the entire pipeline. And what is interesting is that the projection is versioned, has the historization, and a collaboration system. So with the previous slide that I showed you, one typical problem is, what happens if I update something in Patchwork 3D? I will push that change to the pipeline and all software will be updated. All scenes will be updated in every software, so I don't have to redo the work each time. And even more, if in Blender I must change a color, it won't be preserved in Patchwork 3D because this is a one-way connection. But it will change the color for VRED and Unreal. Ultimately, when I make changes in Patchwork 3D, such as moving a part and updating the system, it results in updating Blender, which destroys the specific material color I created in Blender. All this workflow will be completely synchronized, and I will lose no information during the process. The 4 ecosystems are continuously synchronized, enabling collaboration among colleagues at different stages, times, and moments. The digital backbone ensures that all differences between sequences of modifications are effectively managed. I showed you a linear pipeline that is not very impressive, but what is interesting about digital backbone is that you can create any kind of bridge. So you can create any topology, you can go from Patchwork 3D and export to OpenUSD, Blender, and Unreal Engine with the same capabilities. It means that updates will be managed by the digital backbone. Do you use VRED? Okay, no problem. You can create a pipeline from VRED to OpenUSD, Blender, Unreal Engine, and once again, the updates will be managed by Digital Backbone. Why this demonstration? It means that the Digital Backbone, even if we have built and developed it, we want it to be agnostic. We don't want to lock that technology into any one technology. It should work with any kind of product. So we open the technology so everybody can connect to the product and develop their own driver and bridge. In this presentation, we have seen that we can project a Renault Twingo car through 4 different software ecosystems, and it works. We have a live demonstration of that pipeline that is working. Since last year, we have developed 6 working drivers: Patchwork 3D, Blender, VRED, Unreal Engine, V-Ray, and OpenUSD. And we are developing more drivers like Unity, Katia, and Alias that are on the roadmap. You can build your own pipeline with your own rules using Digital Backbone with the Python language. This is very easy. Again, you can develop your own pipeline and you own your own rules. That's why Digital Backbone is unique. So, you can visit the dedicated web page at lumiscaphe.com/laval-virtual-2026 to discover and test it. Here is the next year's roadmap. We are working, as I said, on extending the catalog of drivers and onboarding software editors, even competitors, because I think it's better to have a direct connection with them to develop efficient drivers. But we want to develop and customize open source bridges and connectors to fit users' needs. And if you are interested in that kind of connector, we can work together to explain how to create, in Python, your own drivers or bridges. We also plan to develop an orchestration software above the Digital Backbone. It is very simple to create your own application with a graphical interface that manages all information to orchestrate the workflows. Of course, it's another level, but possible and very interesting to implement. Once again, the idea is to give IT teams the ability to develop complex workflows and complex metastructures that rely on the Digital Backbone technology. Thank you for viewing our presentation. We invite you to visit the website and contact us for demonstrations. We appreciate your interest.